السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, we'll continue hopefully for maybe 10 or 15 minutes talking about variable elimination, and then we'll switch to inshallah a new subtopic. Last time we ended up with knowing how we can use factors to do both inference by enumeration and variable elimination to do inference over base nets. And we said that variable elimination is a bit more efficient than inference by enumeration because we interleave joining with elimination. In enumeration, we do joining for all variables before we eliminate any of them, but in variable elimination, we join one variable first and then eliminate it, then join another, then eliminate it, and so on. And that will make the process more efficient. Now we'll talk about the issue of ordering the variables that we will eliminate. Last time we said that we'll do it in a specific order, any order. Okay. Now we want to know whether the order will make any difference or not. So let's consider this base net that we have here in front of us, and let's say that I want to compute this probability P of xn given y1, y2 up to yn. So this is typical in base nets that we observe the variables that are at the bottom of the network, and we want to infer something about the other variables. So here let's go through two different orders, and see what will happen in each. So let's say that I want to start with the order I want to start with this order, which is x1. I want to start with the elimination of the variables in this order, which is eliminating x1, then eliminating x2 up to xn, then up to xn minus 1, then z. Okay, I don't want, of course, to eliminate xn because that's the variable that is the query variable. So let's start with x1 and see what will happen if I eliminate x1. To eliminate x1, I need to get first all the factors that involve x1. That's what we said in the last lecture, right? We need to join first the factors that involve x1, that has x1, and then we eliminate that variable, which is x1. So what are the factors here? Assuming that we just started with the initial factors, what are the factors that involve x1 here? Any idea? But what are the factors that we have in this network? We have P of z. Okay. We have, for example, for this one, we have P of xn given its parent, which is d, and so on. So these are the initial factors, the CPTs, the conditional probability tables. These are the initial factors. Now, what are the factors that involve x1? Someone raised hand? Yes, Mahmoud. P of z involves x1. So do you see x1 here, Mahmoud? So it doesn't. It will not. It shouldn't be involved in joining on x1 because it doesn't have x1. How can I join on a factor that doesn't have the element that I want to join on? So what are the factors that has x1? What is the conditional probability table that is associated with this node? Mahmoud. Yeah. So do you remember what will be the conditional probability table here? It's the probability of the variable given its parents, right? So the factor here is P of what? Yes, P of x1 given its parents. What are its parents? Z. So that's x1 given z. Does it involve x1? Yes, of course, it has x1 here, right? Involve means it has x1 somewhere in the table. So it involves x1, so that's one factor. What else? Do we have any other factors that involve x1 also? Yes, so that's we cannot say y1. y1 is not a factor. So the factor is p of, yes, so should I say y1 and x1, or y1 given x1? Given x1. Okay, so that's the other factor here. Do you have any other factors that involve x1? No. So we only have these two factors. طيب. You attended the lecture last time, Mahmoud? You didn't. Did you watch it? Not yet. Okay. طيب. Anyone who watched or attended the lecture last time, when we join these two, what is the factor that we will get? Anyone? So what we said last time is that when we have something like this, we will get a factor that has first, before the condition simple, we will have the union of the variables that appear before the condition simple. So we have x1 and z1. Sorry, x1 and y1. That's the union of this and that. Then, after the condition, we put all the remaining variables in these two factors, which is z. So that's now the factor that we will get from joining these two factors. We'll get factor of x1 and y1 given z. Okay? Is that clear? Then, of course, we do the elimination. We get rid of x1. So we'll get a factor that has y1 given z. So that's the factor that we will get after we eliminate x1. Okay, is that clear? Is that clear to everyone? Is that not clear to anyone? Okay. How about the others? Do you have any questions on what we said so far? Type. If we continue and eliminate x2, it will be very similar, right? Because for x2 we will have the p of x2 given z and p of y2 given x2, so it will be very similar to this. And so if we continue in that order, x1, x2, xn, up to xn minus 1, we will get factors of that size. Type. What is the size of that factor? How many dimensions in that factor? When we say factor, as we said earlier, this is like a table, right? Factor means a table of probabilities. So what are the dimensions of that table? We said earlier that the dimensions of that table is the number of variables that change, that are not fixed, that are not observed. How many variables are not observed here in that factor? We have x1, we have y1, we have z. All of them are not observed. So the dimensions here are 3. Okay? Type. Keep that in mind, and let's switch to the other order. Let's go through the order that starts with z. Okay, so I want to now eliminate z first. To eliminate z, we need to get all the factors that involve z. What are the factors that involve z here? Any idea? What are the factors that involve z here? Yusuf? Tell me the factors. X's, by the way, are not factors. The factors are the tables. Not the row, Yusuf. Tell me the probability table. So here, p of x1 given z is a factor. It's not the case that x1 is a factor. We cannot say x1 is a factor. It's p of the conditional probability table that is associated with x1 is the factor. Okay? Very good. So we have p of x yes, probability of x1 given z, probability of x2 given z, and so on until xn given z. Very good. Is that all? That's all the factors that involve z? Nothing else? طيب, Mahmoud, do you have any other thoughts? P of z also involves z, of course, right? We have z here. Okay, so it's all the factors that are associated with these nodes and also the factor that is with z. So this is all the factors that involve z. Now, when we join them, what is the factor that we will get? We get a factor of all the variables, the union of all the variables that appear before the condition, which is x1, x2, up to xn, okay, and also z, because z appeared here, okay, without, it was unconditioned, although it appeared after the condition here, but we get first the union of all the variables that appear before the condition, and then we put the rest after the condition. So here we don't have any other variable, so that the factor will be f of x1, x2, so that's a joint factor between all of these variables. Okay? Any question up to this point? Now that's what, here? Or here? Here, you mean? Say it again. Oh, z given z? Both? No, we cannot. We cannot put the same variable twice, Yusuf. Okay, so Mahmoud, sorry, because I didn't know who was talking. Mahmoud, we don't have the variable twice in the factor or any probability, right? So what we have here is that we start with the union of all the variables that appear before the condition, which are x1, x2, up to xn, and z also. And then after the condition, we put the rest. But we don't have any more variables. All of them appear before the rest, among the factors, of course, that we are joining. All of them actually appeared before the condition. So we don't have anything after the condition. Is that clear, Yusuf or Mahmoud? Mahmoud. Yusuf or Mahmoud? Mahmoud, okay. Any other questions? Mahmoud, stay with me and tell me what is the dimension, how many dimensions we have in this factor. And here we said that we have 3 dimensions. Okay? N plus 1, very good, because we have n x's and 1 and z, so we have n plus 1 dimensions. Okay? So if, thanks Mahmoud. Now, if I want to get the number of rows in that factor, assuming that each of the variables here have 2 values, so the number of rows in that factor will be 2 to the power 3. And the number of rows of that factor will be 2 to the power n plus 1. Of course, if n is more than 2, this factor will be much larger than this factor. Okay? And if you remember, the first order, if we continued, we will not get more than 3 dimensions factor. Here, the first one that we get was n plus 1. So, of course, this order, which is this one, will produce a much larger factor than the other one, which means that it will be more expensive than the other one. Although, by the way, both orders will give us eventually the same values. Yani it's not about whether one will give us a correct value and the other will give us an incorrect value. No, both will give us correct values eventually, but one will be more efficient than the other. And we saw the difference here, okay, between these 2 orders. One gave us a small factor of dimension 3 only. One gave us a factor of dimension n plus 1. When n is large, of course, that factor will be very large. So the order of the variables that we eliminate really matters. The order matters. Okay, the order can greatly affect efficiency, as we see. Now, just to give you an intuition of why that happened, why when we removed z, we got this big factor, but when we removed x1, we didn't get that big factor. When you remove z, actually, before you remove z, all the x's here were conditionally independent on z. And given z, all of these are conditionally independent. But if you remove z, they suddenly become related to each other. And that's why when we removed z completely, now all of these become in one factor. Remember that we will remove z from that, so z will not be there after we join them. So it's like we broke the factor that was protecting us, okay, from the big relationship, from the big dependency. Okay, that one was mediating the relation between all of these x's. When we removed it, now we need to these variables are no longer independent. They were conditionally independent. That's why they were apart, but now they are not. So they are merged together into a big factor. Okay, so that's the intuition. That's the idea behind why we got a big factor out of this order. But the main idea of that slide is that the order matters. Matters not in terms of the value that we will get at the end. We'll get the same value, but matters in terms of efficiency. One order might give me a big factor, which means that the process will be very expensive, and the other might give us smaller factors, so the process will be more efficient. And we don't need even large space in memory to keep large tables. Any questions about that, about this slide? Is it clear? The idea here is clear? Okay. Fine. As we said, the computation and the space complexity is determined by the largest factor. So always the largest factor out of the order of the elimination is the main factor that affects the complexity or the time needed, the time and space needed for that order. And of course, the elimination order greatly affects the size. And now the question is, do we always, given a base net, do we always have an order that will result only in small factors? Okay. Do we always have an order that will be efficient? The answer is no. We don't have such order generally. Yani you might have you might be given a base net in such that it doesn't have any order of elimination of variables to give you small factors. Or you might not have a trivial way to get such order. Okay? There might be the order, but we don't have an optimal way to get it. Okay, it's NP hard problem. Okay, so what is sufficient now is not to get the efficient one, but knowing that the order will matter. So there might be some heuristics that you can use to get better order, but there is no optimal way to get that order. And sometimes even there is no such order that will give you always small factors. That depends, of course, on the structure of the network. Okay, with that, if you don't have any more questions, we will switch now to the last part of that session, which is about sampling. Any questions on that part of the session? Any questions? Everything is clear? You know now how to do exact inference in BaseNet? Okay, so let's now switch to the last part of the session and the last part that we will teach inshallah in that course, which is sampling. Okay, right. I think you see the slides now. Yes, okay. What is sampling? So far, we studied multiple ways for doing inference in Bayes nets, but all of them are exact. What do you mean by that? They give us the exact probability, the exact correct probability. The only difference between them, the inference by enumeration and variable elimination, is that one sometimes is more efficient than the other. Okay, but both give you the exact value of the probabilities that you want. But as we saw, in many cases it is expensive, and even in variable elimination, still the same order of complexity, but in most of the times it is less efficient, but still it might be really expensive. How can we make it even more efficient than variable elimination? This is what we will study, inshallah, in that part, which is using sampling. So sampling is helping us doing what we call approximate inference. So here, when we do sampling, we will do inference, but we will get approximated values of the probabilities. We will not get exact values unless we do the sampling infinite times, as we will study. But generally, this is an approximation algorithm or technique to get the probabilities without computing them exactly. Okay, and that's why it will be very efficient, because if you do it multiple times, you get some approximation. Of course, if you do more computations, you will get closer to the exact probabilities. But the main beauty of sampling is that if you have a budget of time, if you are limited in time, you are given some time in which you want to do the inference, you can run sampling, and when it's the deadline, khalas, you can compute your probabilities in an approximated values. Type. What do we mean by sampling? Sampling is like repeated simulation. We are in the context of Bayes net, of course, and Bayes net is a model of the environment or the world. I can use that model to simulate events. What do you mean by simulating events? We get a value for each variable in the network based on the probabilities that are in the network. What are the probabilities that we have in the network? The CPTs, the conditional probability tables. So based on these local tables, we will draw samples from the network. Drawing sample means it's like a simulation of that network, of an event happening using this network. Okay? So the basic idea is to draw multiple samples. It's not just one sample. We'll do a sample, we'll do another, we'll do a third, we'll have multiple samples. These samples will be coming from the joint distribution of the entire network, because we will go through the nodes, as you will see, given the conditional probability tables. So we'll do a sample that will indicate an event out of that network. Right. Why should we do this sampling? Sometimes we want to learn the distribution, and it is complicated. It is computationally expensive to get the entire distribution. So instead of computing the exact distribution, we will get sample from the network, and from these samples, we can approximate the distribution. Of course, that would be much faster than computing the exact answers or the exact values. Okay? Type. Let's now talk about how we do this sampling. Before we talk about how we do the sampling in a Bayes net, let's talk about how we get just one sample if we are given a distribution, a probability distribution. Given a probability distribution like this one, I have a variable that has 3 values. Each value has a probability. How can I get one sample? How can I simulate getting a sample from that variable? It's really easy and straightforward. We will assume that we will have a random number generator, like the random function in Python. I'm sure that you heard about it or you used it before. So the random function in Python will give us a number between 0 and 1. So we'll call that function. By calling that function, I will get a number between 0 and 1, a random number between 0 and 1. and I will use that number to simulate a sample from that distribution. How? If that number is between 0 and 0.6, I will assume that the sample is red. If that number is between 0.6 and 0.7, then I will assume that it is green. If it's between 0.7 and 1, I will assume that it's blue. What does that mean? It means that I divided the interval between 0 and 1 into 3 sub-intervals. The first one is between 0 and 0.7. Let's say that it's up to here. And I will assume that if the random number is in that sub-interval, then it will be, 0.6, yes. Thank you, Yusuf, I think. Yusuf or Mahmoud? Someone, Yusuf or Mahmoud. انت يوسف واحد يا محمود صح. Yes. Okay. طبعا 10 bonus points for Mahmoud. Okay. طيب. Then this will be خلاص يا محمود. Okay. 0.6. Okay. So that's red. And if that number is between 0.6 and 0.7, then I will assume that this is green. And if it's more than 0.7, I will assume that this is blue. So each of the values here is associated with an interval of the size that is equal to its probability. So the size of the interval for red is 0.6, the size for green is 0.1, the size for blue is 0.3. And that's exactly what we have here. So whenever we get a number, we will map it to the corresponding color. So if I get 0.83, I know that 0.83 is here. So we'll assume that this sample now is blue. Okay? Is that clear? Any question about that? But what if I changed the order here? What if I made the red green first between 0 and 0.1, and then from 0.1 to 0.6 to 0.7 that will be red, and so on. If I change the order, will that matter? It doesn't matter as long as you are consistent. يعني fix it. Get an order, fix it. خلاص. يعني if you draw multiple samples, you fix the order. Don't change the order across samples. Get an order first, any order, doesn't matter which order is. Get an order, put these intervals, make this rules, and that's it. So that will be the order, and you will translate the values into the values based on that order. So if I repeated that 8 times, if I repeated that process 8 times, then I might get something like this. I might get 5 reds, 2 blues, and 1 green. So out of this, the approximated distribution is 5/8 for red, 2/8 for blue, 1/8 for green. Of course, this is an approximation. That's not the exact distribution. Type. When can I get the exact distribution? If I do this sampling infinite times. If I do this sampling a lot, infinite times, then I will be getting very close to the exact probabilities. But this slide is about getting one sample. So whenever now, after this slide, I will not talk about how I get the sample. I'll just say, given that distribution, I will get a sample, and you should understand from that how we do that sample. Okay? Any question about drawing one sample from a given distribution? Any questions? طيب. Okay. Everything is easy يا عبد الرحمن. انت يعني راجل كل الحاجات دي بالنسبه لك سهله يعني. انا بكلم الناس اللي هي يعني ممكن ما تبقاش واضحه بالنسبه لهم. طيب. Sampling. Okay. Sampling is we will study 3 methods in sampling. Actually, I plan to go through 4 methods, but I don't think the time, since the week that is missing, made the really tight time. So we will not be able to cover Gibbs sampling, but inshallah we'll cover the first 3. So let's go through the first one, which is called prior sampling. Remember again, our objective is to do sampling from the base net so that we can get the joint distribution. So that's exactly the objective for prior sampling. Given a base net, I want to draw samples, and from these samples I want to do inference. Instead of computing the joint probabilities, I want to compute that from the samples that I will get. So to draw samples from the base net, I will get a sample from each of the distributions, for a sample for each variable, and we will have to start, of course, from the top and going down, because each variable is dependent on its parents. So I have to draw samples from the parents first, see the values that we get, and based on that we draw a sample from the children. So we'll start here by drawing a sample for cloudy. So for cloudy we have this distribution, so I will draw a sample from it randomly. Now I will not say how, you know that from the previous slides. I will get a sample. Let's say that we got positive here. Green here means positive. All the variables here are binary, so green means positive, red means negative. Okay, so now that means that we got plus C for this variable. Now the next variable will get the variable S, or sprinkler. Now we already know that cloudy is plus C, so the distribution that we will draw the sample for sprinkler now should have plus C. So we will only consider this distribution. So now we will get a sample from that distribution. If that were minus C, I would get a sample from that distribution. But now, because we have plus C here, which is the parent of that variable, we now determine which distribution among these two we will draw the sample from. So we'll draw now a sample from that distribution. We got red, which means minus S. So we got minus S here. Okay. Similarly, we do for that variable rain. We have plus C here, so this is the distribution that we will draw the sample from for rain. So we draw the sample, we got green, which means plus R. Now we want to draw a sample for this variable. Which part of that table will be the distribution that we will draw the sample from? Can anyone tell me? Faisal? Alhamdulillah salama, Faisal. Alhamdulillah salama. Okay. Which part of the table, Faisal? Yes. Yes. So these two entries, right? So that's the distribution that we will focus on. So we'll get, thanks Faisal, we will get a sample from that distribution. Okay, so now we got a sample plus W. Okay, so now this is one full sample. So the full sample now is plus C minus S plus R plus W. Why did we say that this is a full sample? Because that's a full event from the entire network. Now we simulated an event that is happening in that environment. Cloudy, not sprinkling, raining, and the grass is wet. So that's one sample. I can draw another sample. So in the other sample, we got minus C plus S minus R plus W, and so on. So we can draw multiple samples. Okay. Fine. Here is the main algorithm we use for drawing one sample using prior sampling. So we call this method of sampling prior sampling. Here it's called prior because we don't have any evidence. And in doing prior sampling, we don't assume that we have any evidence. So the idea here is to go through every variable and draw a sample from the distribution of that variable given the pairs. And going through all variables, that will be just one sample, the full assignments of all variables. If we want to repeat it, of course, we can repeat that process if we want to get more samples. Now, this process generates samples with a probability. What is the probability of generating one sample? And if we go back to this sample, what is the probability of getting this sample? Knowing that this is a Bayes net, we can compute the joint probability of this sample, right? So this probability, even without knowing the Bayes net, without knowing the Bayes net, let's see through the process that we did, what was the probability to get that sample? We draw from cloudy first, right? From this distribution, so the distribution is P of C first, assuming that this is C, C, S, R, and W. So that's probability of C times what is the probability of getting S after we got C? That S given C, right? So that's probability of S given C. That's what we did, right? We got C, and based on that, we get S based on C. Then P of R given C, then P of W given R and S. So this is the process that we did. We get C from the prior distribution of C, we get S from the conditional distribution of S given C, we got then R from that conditional distribution, we get W from that conditional distribution. Now, if you look at this process, this probability, of course, all of these are multiplied by each other. What is this probability? This is the joint probability of that sample. So that's the joint probability of C, S, R, and W. And that's what we have here. Okay, so let me explain the notation here first. S here means sampling probability, and PS means prior sampling. So that's the sampling probability of that sample using prior sampling. The sampling probability of that sample is based on the way that the process that we used in prior sampling. It is the multiplication of the probabilities of getting this value given the values of the pairs, which is, as we saw, the joint probability. Okay? Any question about this? So that's the joint probability based on the Bayes net. Now, if we repeat that multiple times, if we think that if we do that infinite times, so the ratio of the samples that in which we get this exact values depends on this probability, of course. And for example, if I draw a die, what is the probability of getting 1? It's 1 over 6, right? Because we have 6 faces. Now, if I draw that die 100 times, what is the expected value of the number of the times that in which I would get 1? That should be 1/6 of 100, right? 100 divided by 6. That's the expected number of ones. Of course, I might not get that number exactly. But if I do this drawing, that sample, if I do this sampling infinite times, I will almost get the probability that is 1 over 6. Okay? So this is exactly what we are saying here, that when n goes to infinity, when I do infinite samples, the expected number that I will get, the expected probability that I will get is exactly the probability, the joint probability of the sample. When that's happening, when we say that if we do this sampling infinite times and it will give us the exact probability, remember that this is the exact joint probability. Doing it infinitely will give us the exact probability. We call this consistent sampling. We call this consistent sampling. Okay, so the sampling is consistent if we do it infinite times, if doing it infinite times will give us exact probabilities, which is the case with prior sampling. Okay, because of the way that we draw the samples, which is based on the model of the Bayes net. Any question about that, or any of the previous slides? So you understand now why we call this consistent sampling, because it will eventually, if we do it infinite times, it will give us the exact probabilities. Now let's see an example to show us how we do inference. So using the same net, let's say that we got a bunch of samples. We got these 5 samples out of this Bayes net, and we want to compute P of W. How can I compute P of W? P of W means that I need the probability for plus W and probability of minus W. So inference using sampling is all about counting. We will just do counting. We will not do any multiplications, or except in weighted sampling that we'll talk about next time. But it's very simple. But mainly it is counting. It's about counting. So here, of course, this is minus W. So how many, for computing this probability, we need to know how many times we got plus W and how many times we got minus W. Out of these 5 samples, we got 4 plus W and 1 minus W. So that means that the probability that we will estimate is 4 out of 5 and 1 out of 5. Okay? Are these probabilities exact? Of course not. Yeah, we got them just from 5 samples. How can we get the exact probability? Do the inference using one of the methods that we studied earlier, enumeration or variable elimination. If you do these samples infinite times, you will get the exact, or very close to the exact probability. Okay? Is that clear? So just by counting. Time. Now, of course, this process can also estimate other values. So, if I want to estimate probability of C given plus W, what should I do? P of C given plus W. Now we have a condition. So, let me erase, actually I don't need to erase anything. We have a condition here. So, we should only focus on the samples that have plus W. So, this one, this one, this one, this one. Then we compute how many times C was plus C and C was minus C. So among those that have plus W, because that's the condition, right? So how many times we have plus C here? This one, this one, this one. So we have 3 times plus C, and minus C we have just 1 time. So that's 1. And then we normalize by the sum, of course, so that will be 3 over 4, not 5. Because plus W appeared 4 times, and that's 1 over 4. Okay, so that's the probability of C given plus W. Okay, how about this one? Can anyone do that with me? P of C given plus R and plus W. How would we do it? Anyone? Mahmoud? You mean 3 samples? Okay, so let me erase this because that's now confusing. So which samples we should focus on? First, because we have plus R plus W. Second, and fourth. Okay, then very good. How many plus C and how many minus C? Very good. So it's yes. And how about this? That's what that will be 0. Yes. Okay. So that's this probability. Type. I want someone else to do this with me. Faisal, I think you raised the hand. Yes. Can we do that with me? We don't have any. But what does that mean? The probability is 0? Very good. Excellent answer. Okay, yes, we don't have enough samples, so we cannot say that the probability is 0. We just can say that we cannot compute that probability using these samples. So you either say we don't know, we cannot compute it, or we draw more samples until we get some of them to have the evidence. Okay, so this is exactly one of the major drawbacks of prior sampling, is that sometimes we don't get enough samples to get some of the rare events. Okay, so the rare events might not appear easily. So in that case, as you see, we might not be able to do this probability at all. And that's not 0. When can we get 0? Like in this case. In this case, we got 0. Why? Because we have samples of plus R and plus W, and among them, we didn't get any minus C. That's 0. Of course, this is an approximation. Again, all of this counting is just an approximation. But here we cannot say anything because we don't have any samples that has minus R and minus W. So we cannot say anything about this probability. Next time, inshallah, we'll see how can we address this drawback using rejection sampling and also weighted sampling, inshallah. Type. Any question about prior sampling? Of course, the advantage of it is that it is fast, right? If we can draw as many samples as our time budget allows us, and then we do the inference. If, of course, if we have more time, we can draw more samples. We get closer to the exact values. Any questions? No questions? Everything is clear? Okay, good. Now, before we finish the lecture, I want to talk to you about two things. The first thing is that I posted yesterday a survey for the TA. So it's a survey about the TA. Okay? Please do it. The deadline for it is tomorrow, but I really need it tonight. So please do it as soon as you can. This is the survey, the course evaluation for the TA, for the teaching assistant, who is grading and holding office hours for the course. Please be honest, be fair, be constructive in giving us feedback. Okay? Same thing, I think you received probably also course evaluation for the instructor, for me. Did you receive that? I think you received it. Yes, so please also do it. Please also do it. Don't forget to do it. Please do it fairly, honestly, constructively. Okay? We really make use of that, or benefit from that a lot to improve the teaching for the next time of the course, inshallah. Okay, so that was the first point. The second point is that on Sunday, we will have the last quiz. And the last quiz, as I told you in one of the announcements, is a bonus quiz. So you don't have to do it if you don't like. Still, I will drop one of the five quizzes. And if you attended, then I will drop 2. So that's kind of a bonus here, or one more extra chance for you. The quiz will cover the introduction to the machine learning part that I sent links for the videos for. Okay, so I sent you 2 links for 2 videos. I think they are really informative. The feedback that I got about them is very positive. Please go through them. They are really informative. They will not be covered in the exam, so they are not part of the final exam, but they will only be good for the quiz. And for you also, as this part of AI is very hot now. So knowing about machine learning is kind of a must. Okay, so please go through them and be prepared for the quiz on Sunday. So on Sunday we'll have three actually parts. The first one, I will have a session for you to get your questions about the introduction to machine learning session. Okay, so if you have any questions, we can discuss them. And also we'll have the quiz, and inshallah also we'll continue this sampling part. Hopefully we will finish it by Sunday. If not, we will have to continue on Tuesday, inshallah. But the priority will be for your questions and for the quiz, inshallah, on Sunday. Any questions from your side? Okay, then we'll stop here, inshallah, and talk to you on Sunday. Assalamu alaikum wa rahmatullah.